This video is on acid and base concentration and pH. So to review, an acid in water produces H3O+, or the hydronium ion. An example looks like this. HCl, which is aqueous or dissolved in water, plus water produces Cl- or chloride ions that are aqueous and H3O+. Really, what's happening is the H from HCl is getting together with water so that there are three H's, and it's H3O+. And then what's left behind here is our negative chloride ion. Okay, so a hint. When you see H3O+, think acid. When you see stuff that starts with a hydrogen, honestly, oftentimes an acid. Not always, but often. Like, for example, just plain water, H2O, isn't exactly an acid, although it has acid and base present. Get to that in a second. Okay, a base in water produces OH- or hydroxide. So, an example of this is NH3, aqueous. So this is ammonia, aqueous plus water, liquid, makes OH- aqueous, so hydroxide, plus NH4+. The idea here is the opposite. An H from water is going over to the NH3. And when the H from water goes over to the NH3, water is left with O and only one H to make hydroxide. And the NH3 becomes NH4+. So the acid here gave up its H plus to water. The base here gets an H plus from water. Okay, so hint, when you see hydroxide, think base. So H3O+, hydronium, acid, OH-, hydroxide, base. But pure water always contains a tiny amount of both hydronium and hydroxide. Water is an acid and a base, and it's an extremely weak electrolyte. So, it has these ions in solution. Water does what we call self-ionize or auto-ionization. So one water will give up an H plus to the other water so that you end up with H3O plus. An extra H on one water makes hydronium, and missing an H on the other water makes hydroxide. So there's a small amount of hydronium and hydroxide that's always present in water, but it's always equal. They neutralize each other out. So about 1 out of every 560 million water molecules actually forms ions. So this is a very small portion. The concentration of hydronium or hydroxide ions is 1 times 10 to the minus 7. That's where we're talking about 1 out of every 560 million. So very few water molecules are doing this. And then when they do, all of the acid neutralizes out all of the base. So these neutral solutions are going to have equal amounts of H3O plus and OH-. So neutral water has equal amounts. Brackets mean molarity. So when we see something with brackets, whatever is inside the brackets is the molarity or the concentration of that solution, by the way. Okay, so have you heard about what the pH of a neutral solution is? It's pH 7. Now, it's no coincidence that the H3O plus is equal to the OH minus, and that's equal to 1 times 10 to the minus 7 for a neutral solution. So H3O plus equals OH minus equals 1 times 10 to the minus 7. And there is this tricky little 7 here. That's the reason that pH neutral is a pH of 7, is because of this. So when we have a totally neutral solution, all the H2O plus equals out all the OH minus. Both of their concentrations is 1 times 10 to the minus 7, and the pH is 7. So let's dive into the math and kind of try to figure out why that is, or learn about why that is. Okay, so the acidity and basicity of a solution is often expressed as pH. It's sort of for power of hydronium. That's, the idea of where the, sorry, I don't know, hit my keyboard. Power of hydronium is where that comes from. Okay, so The formula for calculating pH is that you take the negative log of the H3O plus, or the hydronium ion concentration. The inverse of that equation is to find H3O plus, you raise 10 up to the minus pH. 10 raised to the power of the negative pH. It's just the opposite or the inverse of that equation. So if we do the pH of neutral water, what we would do is we said that remember how we said that the H3O plus, on the last slide, we said the H3O plus concentration is always equal to the OH minus concentration, and both of those are always 1 times 10 to the minus 7. That's their molarity for neutral water. So this is when it's neutral. So what if we tried to do this? Let's try to take the negative log of 1 times 10 to the minus 7. So let's get out our trusty calculator. I'm going to use this example online, TI-30XA calculator. Okay, let's try this. We're going to take the negative log of 1 times 10 to the minus 7. Well, first we need to calculate that 1 times 10 to the minus 7. So let's go 1 times 10, and then let's do y to the x. Let's do 10 raised to the, because 10 is our y. Next, we're typing in our x. So 10 raised to the 7, but let's make it negative. So now we're raising 10 to the negative 7. So that's 10 to the negative 7, or 1 times 10 to the negative 7. We need to take the log of it, and then don't forget it was the negative log. And so we're back to our neutral pH 7. So, so what we see there is that the pH, or the negative log of 1 times 10 to the minus 7, is just always 7. That's how this math works out. This log, by the way, is a log base 10 scale. So what it's telling us is that a base 10 scale means that every change in a pH number is a change in concentration times 10, right? It's 10 times more or less concentrated. So in order to find pH, you need to have the hydronium ion concentration first. So let's just look at the scale a little bit, and we'll fill in this table. So here's the idea. Just like the exponent here, if it was a whole number, gave us the pH, we can do some examples. If you have a 1 in front of your H3O plus concentration, then your exponent tells us your pH. In other words, if we take the log of 1 times 10 to the minus 10, we get a negative 1. And when we switch the sign and make it a negative log, we get a 1. So we could try it together. For an H3O plus of 0.1, that's the same as 1 times 10 to the minus 1. And so we could just go ahead and try that in our calculator. So 0.1 is just 1 times 10 raised to the 1 negative, or minus 1. That was 0.01, which we saw in the table. We were supposed to have 0.01. Take the log of that and you get negative 1, and then you switch the sign. So again, where are we at in our table? Well, we saw that 1 times 10 to the minus 1 is the same as 0.1. Took the log of that and we got negative 1, and then we switched the sign because there's negative in front of it. 1 times 10 to the minus 2, when you take the log of it, is negative 2, and switch the sign, and it's 2. So again, if we have a 1 in front of our scientific notation, then our exponent actually tells us our pH. That's kind of slick. So 0.001 is the same as 1 times 10 to the minus 3 molar. Take the log of that and you get minus 3, and switch the sign and you get 3. 0.0001 is 1 times 10 to the minus 4. Take the log of 1 times 10 to the minus 4, and you get minus 4. And then switch the sign, and you get a pH of 4. So here's the big thing, though, to remember. If you have a solution that is pH 3, it is 10 times more acidic than a pH of 4. If you have a 2, it is 10 times more acidic than a 3, but the 2 is 100 times more acidic than the 4. If you have a 1, it's 10 times more acidic than your 2. But versus your 4, your 1 is actually 1,000 times more acidic. And so that's really kind of exciting. And actually, a pH 1 versus a 7 is a difference of 1,000,000 times more acidic. In other words, a 1 is 1,000,000 times more acidic than a pH 7. It's really kind of fascinating. These factors of 10 that make it super interesting. Okay, so the lower the pH of the solution, the more acidic the solution. And the higher the pH, the more basic the solution. 1 pH unit corresponds, like I just said, to a factor of 10 difference in acidity. pH can be negative, very acidic, or it actually can be larger than 14 and very basic or alkaline. So another word for basic is alkaline. And again, when I was talking about the difference in factors, these are a 10x factor, but when you move 2 pH values, it's 100x. 3 pH values, and it's 1,000 times more acidic, and so on. So those are some really big, drastic differences. That is kind of cool. Okay, so let's do some practice. Where can I move myself here? How about that? Calculate the pH of the following solutions. Label the solutions as acidic, basic, or neutral. This is a great place to pause and try as many of these as you can. Okay, we did an example like the first one, 1 times 10 to the minus 7. Well, we know that that's a pH of exactly 7, and we know that that's exactly neutral because there's a 1 here. Okay, 1 times 10 to the minus 1. Well, again, that exponent, since there is a 1 here, tells us this is a pH 1, and a pH of 1 is very acidic. When H3O plus equals OH minus, we know that only happens in a neutral solution. By the way, then we know that the H3O plus is 1 times 10 to the minus 7. So it's the same as the first one. pH is 7, and that is totally neutral. Okay, how about in this next one? We have an OH concentration, a hydroxide, and a hydronium ion concentration. Probably the easiest thing to do for this one is to say, well, I know my H3O plus. Why don't I use that to calculate pH? So I'll go, okay, pH equals negative log of 1 times 10 to the minus 6. Or, hey, I can notice this is a 1, and so my pH will be 6. That's less than 7, so that one's acidic as well. Okay, here we've got an H3O plus and an OH minus hydroxide and a hydronium ion concentration. I'd probably do, pH equals negative log of this H3O plus concentration, or the negative log, of point, and then I go, there's 1, 2, 3, 4 zeros, point, 1, 2, 3, 4, 1. I could also notice that if I put that in scientific notation, this is actually, if I move the decimal 1, 2, 3, 4, 5 places, this is actually 1 times 10 to the minus 5 for an H3O plus concentration. That's going to make pH 5. Or I could put this in my calculator. It's really up to you. If you put negative log of 0.00001 in your calculator, some people would do that. But we get a 5, and this one is acidic as well. Gosh, we've seen only acidic or neutral so far. That's suspicious. What about this next one? H0 plus is 1 times 10 to the minus 13. Oh, there we go. There is a 13 for pH, and a 13 is basic. Oh, so there's a basic example. You know what? I'm thinking there's one thing on this last slide I wanted to mention, so I'm going to do it right now. One thing I wanted to mention is, when we are at the basic end of the spectrum, that means that H3O plus concentration is really low and it's much, much less than hydroxide ion concentration. So hydroxide is high when it's basic. And it's the opposite over here when it's acidic. When it's acidic, it's the opposite. H3O plus is really high, and that's much, much greater than OH minus or hydroxide ion concentration when it's acidic. So this is a teeter-totter, right? When you have an acidic solution, H3O plus is really high and OH minus is low. When you have a basic solution, OH minus is high and H3O plus is low. So this is like, a teeter-totter that's doing this back and forth. Okay, let's use our calculator to find some pHs. Now look at how H3O plus equals 1.9 times 10 to the minus 7. Some people might just put 7 here, but that would be incorrect because this is not a 1. So anytime that your first number here is not a 1, you're going to have to break out and use your calculator. You're going to have to actually calculate the negative log. So pH equals the negative log of H3O plus, or the negative log of 1.9 times 10 to the minus 7. We could do this one on the calculator together. So 1.9 times 10 to the minus 7. We can break out the calculator. Let's do 1.9 times 10, y to the x. 10 was going to be raised to the 7, but it's to the minus 7. Okay, so there's our value, our concentration. We need to take the log of that, and then remember that it's the negative log. So we get 6.72. Okay, so that answer was 6.72. Why don't you pause and put this one in your calculator? So we have the H3O plus concentration. pH is going to be the negative log of 7.4 times 10 to the minus 9. So try that in your calculator. You should get 8.13 for pH. Okay, so there's our two pHs. Acidity and basicity can also be expressed in pOH. It's the same thing, just for hydroxide ion concentration. It's like the power of hydroxide is the negative log of the hydroxide ion concentration. And the inverse equation is that you can actually do OH minus, by the way, is 10 to the minus pOH. But oftentimes, it's important to just know that pOH and pH together, they add up to 14. So oftentimes, if you want to find pOH, you might take 14 and subtract out whatever the pH is, because pOH and pH together have to add up to 14. So there's a lot of different ways to look at these equations. But I hope that this introduction helps you with just some of those ways.